right, our next section here related to switching is going to focus around layer 2 security mechanisms, and just as importantly, what are different types of layer 2 vulnerabilities in the Ethernet network, and then what are the tools that we have available in the Cisco Catalyst iOS in order to prevent these type of attacks. Now, as you can imagine, in the world of network security, there's tons of different vulnerabilities and tons of different attacks that we could be talking about. We could do a full week or even multiple weeks talking about just different network attacks and application attacks and how to mitigate them. For this section, we're mainly going to be focusing on layer 2, things that would go on in the Ethernet LAN, attacks on the CAM table or ARP poisoning, DHCP poisoning, things that are typical attacks that go on at layer 2 that are fairly easy to prevent with the different tools that are in iOS, but they're definitely going to be a big issue if you do not know that these problems are there in the first place, that these type of problems need to be addressed. So first off, in security, before we can prevent any of these type of problems, we need to know what are the possible common attacks out there. Now, a lot of the attacks that we're going to focus on are going to be known as man-in-the-middle attacks, or MIM. And man-in-the-middle doesn't necessarily refer to an individual methodology of attack. It refers to basically the final result. Now, in a man-in-the-middle attack, whether it be layer 2 or layer 3 on the local LAN segment or even over the WAN, over the internet possibly, the goal of the man-in-the-middle attack is for the victim to accidentally send traffic that is going to a legitimate destination. So the victim here is trying to send traffic to the internet. The attacker is somehow going to get the victim to redirect the traffic to itself before it is forwarded on to the final destination. Usually the goal of this type of attack is some sort of sniffing, like password capture or maybe financial information capture. And the problem is that a lot of the times this is going to be transparent from the victim's point of view. So the victim goes to their banking website and they put in their social security number or whatever information, and they do get the legitimate replies back from the website. So from their perspective, it doesn't look like anything is wrong, but somehow the attacker has inserted them in the layer 2 transit path, which means that any unencrypted information they will be able to sniff out of the layer 2 and layer 3 frames. So we'll spend some time talking about what are the specific implementations of man-in-the-middle. How can we do this from layer 2 point of view by doing ARP poisoning versus doing a DHCP poisoning or a layer 3 or layer 2 type spoofing. Now, a little bit lower level than that, first couple attacks that don't necessarily relate to man-in-the-middle but do relate to layer 2 Ethernet. First one is considered a VLAN hopping attack. Now, I talked about this briefly when we talked about the dynamic ports on the switches and how with the dynamic trunking protocol, the switches will automatically try to negotiate trunk links on all of the dynamic ports, whether they be in dynamic auto or in dynamic desirable state. Now, the goal of a VLAN hopping attack is basically for the attacker to be able to insert frames into a different segment of the Ethernet network than they are supposed to. So let's say that they are in VLAN 10. VLAN 10 is for our normal user data, and VLAN 20 is for servers. The goal of the VLAN hopping attack would be for the user to insert their traffic into VLAN 10 on their normal port into the switch block, but then somehow get it to actually go into VLAN 20 directly from a layer 2 point of view. Now, there's generally two variations that the switches could be susceptible to this type of attack. First one is going to be related to dynamic trunking protocol. So if the switch that is going down to the end host is configured in either dynamic auto or dynamic desirable mode of DTP, the attacker simply needs to negotiate DTP with them, and then through .1Q tagging or ISL tagging, they can simply insert their own frames into whatever particular VLAN that they choose. Now, by doing some basic layer 3 segmentation, VLAN hopping attacks for the most part are going to be defeated, because if the VLAN is only local to your individual access switch, or maybe between a few access switches and a distribution switch, VLAN hopping is not going to accomplish a lot. But in a large flat layer 2 network, it definitely can be a potential problem. Now, the other variant of this would be for double tagging frames as .1Q, meaning that they put an outer frame as a garbage tag that could be any VLAN number, then an inner tag that is the destination VLAN that they are trying to reach. Now, most of the Catalyst iOS switches are not vulnerable to this attack based on some very simple configurations when we connect the access ports to the end hosts. If we configure the switch as the switch port as switch port mode access, meaning it is not a dynamic port, it is not a trunk port, anytime a .1Q tagged frame is received, the switch is simply going to throw it away. Now, this vulnerability is for when a switch is not configured in access mode, or for some other non-Cisco switch or possibly version of code that is vulnerable to not throwing away frames that have .1Q tags. So the Cisco Catalyst iOS default behavior is that when a trunk frame, so a .1Q frame, is received on a non-trunk port, it should be removed. Some other switches differ in this behavior where they don't discard the frame, they simply remove the tag. Now, by removing the tag, what's actually happening is that they are removing just the outer tag, which is basically just a garbage padding, and revealing the inner tag, which is the destination that the attacker is trying to get to. So VLAN hopping mitigation is pretty straightforward as long as you know that the problem is potentially there. One of the key points is that you don't want to use dynamic ports. Now, using dynamic ports does make it easier for deploying trunking or for deploying IP telephony, but the problem is you're getting ease of management with the negative of having the security vulnerabilities. So simply, as long as you configure the port as switch port mode access, then it is not going to be susceptible to VLAN hopping. Now, an additional protection against this type of attack is to configure unused ports not to be in VLAN 1. And the reason why is that, like we saw on our first day, when we boot up the switches by default, all interfaces will have the access VLAN assignment of VLAN 1. So this means if someone brings a new switch in and plugs it into the network, those ports potentially would be in the same broadcast domain as all other unconfigured ports in the network. So generally, it's a good recommendation not to use VLAN 1. What you would want to do instead is that the unused ports in the network, you would want to assign them to a suspended VLAN. So a VLAN that's not running spanning tree and basically cannot create a CAM table. So then you know which particular ports are actually valid for sending traffic into the network. But in the end, it really ends up being a toss-up between how much management overhead do you have and how much ease is for the users. So if you have users going around and plugging into all sorts of different ports and the network is very dynamic, then maybe this is not a good solution. But if you have a very high security environment where you know exactly which ports are supposed to be used, then it's a good idea to basically disable all of the unused ones. Okay, there's a question here. By double tagging the frames, they can only send data but not capture it. Correct. So in either case, the VLAN hopping attack is more likely to be some sort of layer 2 denial of service. So if we're just blindly flooding frames into the network and forcing them to get into a different VLAN, we're never going to be able to receive a response back because the originating host is not legitimately in that VLAN. So if the attacker is supposed to be in VLAN 10 and they're trying to hop over to VLAN 20 to attack the servers will receive the traffic, but then they can't reply back to the originating host. Now, one variation of this type of attack is against the CAM table or the MAC address table of the switches itself. Now, we talked about how the behavior of the layer 2 switching works, and how the bridges use the source and destination MAC addresses to populate their switching tables, the CAM table. So once the switch originally boots up and no traffic has been sent through it, the first frame that it receives, it looks at the source address and correlates that particular host source with that port. So meaning if host A sends a frame into the network on port 1, the switch now knows that MAC address A is located on port 1, and it floods towards the destination, basically treating the frame as a broadcast to try to solicit a response back in to figure out where the destination's MAC address. So the ultimate goal of this flooding process is that we build a unicast forwarding table so the switch moves the frames just between the interfaces where the source and the destination are. Now the problem with some platforms is that if the CAM table runs out of memory, the switch doesn't know what to do with the rest of the frames, and it starts treating everything like broadcast. Now there's some very simple attacks that you can implement in order to fill up the CAM table. One of them is a command line utility called MACOF, M-A-C-O-F. And you can use a lot of these utilities, whether they're in, most of them are Linux or Unix based. Some of them you can run as ports for macOS. But you can use these on your own network or in your test lab to check for these vulnerabilities to make sure that your implementations to prevent them are actually working. But basically what the tool does is it just sends traffic to random destination MAC addresses to try to fill up the CAM table so that you can perform the VLAN hopping attack. So if the switch runs out of memory, it doesn't know what to do with the rest of the frames, and it just floods them everywhere. So you're essentially turning the VLAN into a hub. Now, some platforms, this could also cause the traffic to leak between the VLANs. In other variations, it would just cause the individual VLAN itself to be one flat broadcast domain. So for example, if you fill up the CAM table for VLAN 10, then every new frame in VLAN 10 you send into the network, it gets flooded out everywhere. So usually this is either the indication that you have some sort of attack going on, the MAC flooding attack, or it could potentially be just that your layer 2 network is too big. So like we saw on these 3500 switches, when you look at the SDM template, the switch database manager, tells us how many MAC addresses we can have in the CAM table. So once we breach that threshold, the switch is not going to know what to do with the frames, and it's going to flood them everywhere. Now to prevent this, there's a feature in the Catalyst iOS and in the older Cat OS as well that is known as port security. Port security is designed to limit the number of MAC addresses or the specific source addresses that are accepted on a per port basis. So with the MAC flooding attack, we're trying to fill up the CAM table with thousands and tens and thousands of MAC addresses. Now, port security can prevent this simply by putting a limit saying that I will only allow one MAC address, or maybe I'll only allow 3 or 4 MAC addresses on the port. So we can specify how many MAC addresses, we can specify what the actual MAC is supposed to be. So if we want very, very strict security, we could take an inventory of the MAC addresses of every single desktop, of every phone, of every printer, of every basically end station in the network, and then configure the switches only to allow those MAC addresses per port. Now, once a violation occurs, meaning that there are more MAC addresses than you allowed, so if we limit it to 1 and then the second MAC address comes in, or there's a different MAC address than you specified, so if we said only MAC A is allowed in, but then MAC address B comes in, then port security can take a couple different actions. And this is called the violation mode. Now, normally, the port is simply going to be shut down when the violation occurs, and it goes into a state that is known as error disable. Error disable basically means that the port is not administratively down, but wasn't manually shut down, but it's been disabled for some sort of error condition. So we're not going to spend a lot of time looking at this on the command line. I will go through a little bit later where this is located in the documentation, and then you can either look at the examples in the documents or try some of this stuff out on the switches yourself. So either the result of this, we're shutting down the port, or we could filter the traffic and then generate a logging message. Logging messages being either syslog for the system logging service or with the simple network management protocol with CCNP. Now this is typically common also in an IP telephony environment where you would use port security to limit the MAC addresses on the port, one of them being the phone, and then one of them being whatever the desktop or the laptop is beyond the phone. And we'll come back to this in a little bit later this afternoon when we get to layer 2 quality of service and layer 2 QoS trust boundaries. In IP telephony environments, typically you would have 2 MAC addresses on the port. Okay, so now we get into more of our application level attacks that are going to be related to the layer 2 network. And the vast majority of these, the purpose is that we want to end up in a man-in-the-middle type situation where there's some attacker who is on the local layer 2 LAN on the same segment as the victim. They're trying to convince the victim to send the traffic to them before it goes on to the final destination. So again, here a victim is trying to send traffic out to the internet. The attacker is trying to get it redirected to them before it goes out to the internet. Now, one variation of this is based on DHCP. Vast majority of layer 2 Ethernet LANs, as you can imagine, use some form of DHCP in order to do the address management. So the host comes onto the network or the phone comes onto the network. It asks the DHCP server for an address. The DHCP server is going to lease it based on their particular scope that they are allocated. Now, one of the potential problems with this is that the basic DHCP protocol does not have any security built into it. Okay, this means that there's nothing stopping an attacker from leasing all addresses in the scope. And there's going to be some finite limit to the amount of addresses that are in the scope. So let's say, for example, that our network is a /24. Assuming that we have the 0 address for the network, we have the 255 address for the broadcast, then we're going to have some address on there for the default gateway. Let's say it's .254. This means that most likely at a maximum, we're probably going to have 253 addresses in the scope. A best case scenario, that's going to be probably the largest size of the scope on a /24 network. So the attacker in this type of case, they simply send out 253 DHCP requests. And the server keeps offering them over and over and over until the entire address space is depleted. Now, once the space is depleted, there's 2 options that the attacker can do. They could simply do nothing, in which case the victims are starved of a DHCP lease. This would be a basic layer 2 denial of service against them. Because the client plugs into the LAN, the DHCP scope is already depleted, they can't get an address, and then they can't route traffic into the network. So this is one possibility just from denial of service. The other possibility is that once the scope is depleted, the attacker starts running their own DHCP service. Now, if we look at this from the perspective of this diagram, let's assume that somewhere beyond router 1, we have our DHCP server. Normally, what's going to be happening is that the hosts on the LAN are going to send out broadcasts. They're going to the all 255 address. And this is going to be a boot key request. Okay, so it's a UDP broadcast. It's trying to get a lease from the DHCP server. So the router receives this. It's going to forward it on to the DHCP server. So we're doing something like an IP helper address to forward the UDP broadcasts. DHCP server is going to reply back with an offer, and then the legitimate host is going to accept that. Now, inside this DHCP offer, most likely, the victim is going to get an address. So let's say it gets 10.0.0.1. And it's also going to get a gateway assignment. Let's say router 1's address is 10.0.0.54. Plus other minor options, maybe DNS, maybe TFTP server for an IP phone, maybe the call manager address. But at a minimum, we're probably going to have at least the address and the gateway. So now this host knows that when it wants to send traffic outside the local segment, we need to do a layer 3 to layer 2 resolution for the default gateway's address. So in other words, we need to figure out what is the MAC address of 10.0.0.254. So the victim is then going to send out an ARP request. Okay, normally the router would reply saying, this is my MAC address, this is how you're going to forward the traffic. Now with the DHCP starvation attack, instead the attacker keeps sending all of those requests until the full scope is depleted. Now once the scope is depleted, the victim sends out the request, and since this is a UDP broadcast that's going to everyone on the VLAN, the attacker then sends a reply with a legitimate address from the pool. So the victim here still gets assigned 10.0.0.1, but it replies with its own address as the gateway. Let's say 10.0.0.2, which is the attacker. Now the attacker already knows what are the other options that are supposed to be in the DHCP allocation because it got the legitimate allocation from the real server. So it knows that router 1 really is the default gateway, and it knows the DNS server, it knows whatever other options are assigned in there. But the only thing the attacker has to do is try to trick the victim temporarily to send the traffic to the attacker. The attacker can then forward it on to the final gateway, and it's going to go out to the legitimate destination. Now, in most cases, the flow of traffic is only going to go from the through the attacker on the outbound path, but still at least some of the traffic is going to get redirected to them. But from the victim's point of view, they have no idea that this attack is going on. And if we were to compare the speeds of the LAN at, let's assume this is 100 megabits per second, versus the WAN, even if this is a DS3 link at 45 megabits per second, the additional latency that it's going to take the traffic to go through the attacker is probably not going to be noticeable from the victim. Okay, is everybody up with me up to this point as to what the problem is with the DHCP attack? Okay, so the attacker is trying to trick the victim to send the traffic to itself first before it gets forwarded on to the destination. Now, port security is another way that we can prevent this, and it has to do with how the DHCP requests are sent out. Now, most of the time, a DHCP server will only allocate one address, one layer 3 IP address, per layer 2 MAC address. So this means that if the attacker has MAC address A, and they send that information up to the server is going to say, you already have a binding, I'm not going to send you a new offer. So what the attacker does is just vary inside the layer 2 Ethernet header what the source MAC address was. Because they're not really legitimate allocations anyways. The goal is just to try to deplete the whole DHCP server space. Now, from a layer 2 switching point of view, port security could potentially fix this by saying we're going to limit the amount of MAC addresses on the port. If we say that there's only supposed to be one source MAC address per port, then when the attacker sends the second request or the third, fourth, fifth, all the subsequent requests, the layer 2 switch is going to just discard those frames, or it's going to shut the port down. Because now we're looking at filtering based on the number of MAC addresses on the link, not necessarily the specific MAC address that we're trying to allow. Now next we get to a little bit more sophisticated version of this starvation, is when we implement port security to try to limit the number of source MAC addresses, but the attacker's implementation doesn't use the source MAC address to try to do the allocation binding. Okay, so again, in the previous case, the attacker sends a bunch of DHCP requests sourced from unique MAC addresses. They're sourced from all different MACs. Port security stops this because it says only one source MAC address is supposed to be on the port. But in the DHCP specification, there's a field that is known as the client hardware address. inside the actual payload of the DHCP application, and you can use this field instead of using the actual source MAC address of the packet. So in this case, the attacker keeps their own source MAC address the same for every request, but they keep changing the client hardware address or the client ID inside of the request. So port security fails at preventing this because it only sees one source MAC address. The final result is that we have the starvation. So to prevent this type of attack in both cases, we need to add some application level awareness down into the layer 2 LAN. And this is a feature known as DHCP snooping. So when DHCP snooping is on, this would be on the access switch typically, connected down to the end host. The access switch is going to be listening for UDP broadcasts going to the DHCP port, and it's going to listen to the bidirectional communication between the client and the server. So it means that the layer 2 switch, even though it's just doing basic VLAN operation, it's looking all the way into the application level of DHCP, and it understands what the communication is supposed to be. So it's a type of network-based application recognition that is specific to the DHCP application. Now what the switch does is, first off, it listens for the request, the DHCP request, come from the client. Based on this, the switch now knows where the client is located. It then hears the DHCP offer come in from the server. Now the switch knows two things. It knows where the client is located. It knows where the server is located. It takes the source MAC address that came from the client. It takes the IP address from the binding, or actually the offer from the server, and it builds a mapping table. Okay, we call this the DHCP snooping binding database. Basically, it's an association of the client MAC address to the IP address that the server offered. Now, once an individual client is associated into the database, the switch is going to drop all subsequent requests from that particular client. So it means that once the attacker gets its very first allocation, subsequent allocations will fail because the switch says there's already an allocation on that particular port, and it's inside the binding database. Okay, so this is going to prevent against the starvation attack, because now the switch is saying you can only have one allocation per port, per host. Now, what this will also fix is the what we call here the rogue DHCP server. This is basically where the attacker is running its own DHCP service. So regardless of whether the legitimate space is depleted, the way that DHCP works is that for a single request that the client sends out, you can receive multiple offers back in. But the way that you actually see it in practice is that usually whatever offer is received first is the one that the client is going to accept. So if we look at this from the point of view of our diagram here, let's say, for example, that the attacker is running the DHCP service, but then there's also the legitimate DHCP server somewhere out there in the network. So the victim sends out the request. If the attacker sends out a reply, it's highly likely that the attacker's reply is going to get back to the victim before the legitimate server's reply is, because we simply have less latency to go over the same local VLAN than we do to route possibly multiple hops or even possibly over the WAN to get to some sort of centralized DHCP server. So now we need to figure out a way not only to make sure that there's only one binding per host, we need to make sure that illegitimate replies are now denied. And DHCP snooping is going to do both of these for us. So once snooping is configured, we tell the switch which are the quote-unquote trusted ports. So the trusted port is where the server replies are supposed to be received in. So in that previous diagram with router 1, the victim and the attacker, the trusted port would be the one that is connecting to router 1. Because if we look at the reverse path of where the legitimate servers traffic would go back to the client, from the layer 2 switch's point of view on that VLAN, it would be received inbound from router 1. So for all other non-trusted interfaces, the layer 2 switch is automatically going to discard any replies. So it has dual functionality here. It's making sure that we only have one binding per port, and it's putting that information into the DHCP binding database, and it's also stopping rogue replies from coming from non-trusted interfaces. Now, the only problem with this feature is that you need to make sure that you have the software support for it. So not all switches are going to support this, in which case you could get a similar workaround where you could use just layer 3 access lists. So DHCP requests go to UDP port 67, and DHCP replies go to UDP port 68. So you could have some kind of hacked solution that basically says you will only allow destination port 68 traffic to come in from the port that is attached to the router, or to where the DHCP server is located. And then you would not allow port 68 traffic going to port 68 to come in from the other ports. So you could use port-based access lists, or you could use VLAN access lists, but the ideal solution here would be to use just the dedicated DHCP snooping feature. And there's an important point here in Vishal's question. If there are multiple switches, would you then need to trust the trunks of the switches where the routers are connected? Correct. So if we have a hierarchy of switches, you want to trust the port where the reply comes back in from the legitimate server. So let's say, for example, that we have 2 access switches, a distribution switch, and then the actual DHCP server. The request is going to come in somewhere from the client, go up towards the distribution, and then over to the DHCP server. When we do the trusting, we want to make sure it's in the reverse direction. So the distribution switch would want to trust that port, and then the access switches would want to trust these ports as the replies are coming back in. So you would generally want to do this anywhere in the layer 2 transit path from your end hosts up to the DHCP server itself. But as you can imagine, there is going to be some additional processing overhead, because now all the switches are doing an IP address to MAC address binding for all client traffic that is going between the two of them. Okay, the next variation of this type of man in the middle is to skip over DHCP completely and just try to convince the victim to use the wrong MAC address when they are sending an ARP request or an ARP reply across the network. Now, as we saw in that topology, the victim, the attacker, and the router, in a legitimate situation, the victim sends out an ARP request trying to figure out what is the MAC address that is associated with the default gateway. So router 1 would reply with whatever the MAC address of its interface is. So now the host, the victim, knows the legitimate MAC address binding for the default gateway's IP address. Now the problem you can run into is that just like DHCP, there's no built-in safety guards to make sure that the ARP reply is actually coming from the legitimate device. Now, Address Resolution Protocol supports something known as a gratuitous ARP, which basically means an ARP reply that was sent without someone requesting it in the first place. So an ARP spoofing attack is basically when the attacker keeps sending illegitimate ARP replies, or basically gratuitous ARPs, over and over and over to try to corrupt the ARP cache of all of the devices on the segment. So if we look at this from the diagram point of view, let's assume that router 1 has an IP address of 1, and a MAC address of A. The attacker has an IP address of 2 and a MAC address of B. So normally what's going to happen here is that the victim sends out the ARP request. The ARP request, router 1 replies. It says, my IP address 1 is bound to MAC address A. So now in the ARP cache of the victim, it says IP address 1 is bound to MAC address A. So once that request and reply happens, now the attacker starts sending tons and tons of replies. These are the gratuitous ARPs, or the unsolicited ARP replies. And in that reply, the attacker says IP address 1 is actually MAC address B. So we're not trying to change what is the layer 3 destination or anything to do with the IP address. The attacker is just trying to get the victim to misassociate the default gateway's IP address with its own MAC address. So now what happens when the victim actually sends the traffic that would normally be going towards the default gateway, the traffic is trying to go to the internet, the victim sends it to the destination MAC address B. The attacker rewrites the frame with the legitimate destination A. It's forwarded on to router 1 and then on to the final destination. But again, from the victim's point of view, it's unlikely that they will notice that additional latency, because we're looking at LAN speeds of 100 megabits per second or higher, maybe even gig-E, as opposed to the much slower WAN speeds. So now we need some way, in addition to prevent the DHCP servers from getting attacked, we need to make sure that the ARP requests and ARP replies are legitimate. And this is with a feature that is known as Dynamic ARP Inspection, or DAI. Now, Dynamic ARP Inspection is going to work along with DHCP snooping and the information that DHCP snooping built into its binding database. Now, remember, when DHCP snooping is on, the switch listens for the request coming from the client, and it listens for the reply coming back from the server. So now the switch knows what is the host's MAC address and what is the host's IP address. Now, based on this, the switch's logic says, well, if this is the legitimate MAC address and the legitimate IP address, I can now correlate this with ARP requests and ARP replies to make sure that the replies actually match up with the snooping binding database. So in this case, once DHCP snooping and dynamic ARP inspection are on, the switch is listening not only for all DHCP traffic, but also for all IP ARP traffic. So when the ARP reply is received, if the switch sees that it does not match up with the binding database, so it's a malformed reply, it's an illegitimate reply, the switch simply drops it. So no matter how many gratuitous ARPs or unsolicited ARP replies that the attacker sends, the switch is going to drop them and they're never going to get back to the victim. So typically these two features are run in conjunction with each other, DHCP snooping and dynamic ARP inspection. Now you could technically run them separately, but the problem is dynamic ARP inspection needs to know the IP address binding, the IP address and MAC address binding. So if you had a situation where you were not running DHCP, you would need to create a big access list on the switch that associates each IP address with its MAC address. So otherwise you use the DHCP snooping database, plus you'll have a few static entries in there that would represent things like the routers. So anything that has a static IP address on the link. Okay, the next variation here doesn't relate to DHCP and does not relate to the ARP process. This is simply when the attacker is modifying their MAC address in the layer 2 header or modifying their IP address in the layer 3 header in order to pretend to look like someone else in the network. So these are used typically in attacks against TCP, where you're trying to get someone to to think that you are the destination server they're trying to reach. So let's say, for example, I go to www.ine.com, and once I send the DNS resolution, I get back some IP address. Okay, I now know that this IP address is corresponding to that server. If someone in the transit path starts sending me packets sourced from that same IP address, I have no way to tell, is that really the legitimate server, or is it someone trying to spoof that source address in the network? Okay, so this can happen from a layer 3 perspective with an IP address spoofing, or it could happen from a layer 2 perspective with a MAC address spoofing. So the key here is that from the victim's perspective, it looks like whatever the legitimate host is, whether the host be the default gateway or whatever final destination that they are trying to reach. So now we take the logic of the DHCP snooping and the dynamic ARP inspection one step further into a feature that is known as IP Source Guard. So with IP Source Guard, we're using the same table that was built by DHCP snooping, but now we're going to use it for all traffic, not just for the DHCP packets, the ARP packets. It's going to be everything. So every time a frame goes to move between interfaces, the switch looks at the source MAC address and the source IP address and makes sure that it matches up with the DHCP snooping database. So think of it like an automatic access list filter that is dynamically learned based on the DHCP requests. So ideally, if the switch has enough resources, you would want to run all three of these features at the same time: the DHCP snooping, dynamic ARP inspection, and the IP source guard. Now, in the case that the switches don't support the IP source guard feature, port security is going to give you some minor protection against this. If you know the specific MAC address that is supposed to be on the interface, then you can configure the filter to only accept that particular MAC. So generally, it's a good idea to do some sort of port security limitation to make sure that there's not 10,000 MAC addresses on one individual interface. So if some of your ports go to shared segments of the network, maybe you'll allow 4, 5, or 6 MAC addresses, but you probably would not want to allow 1,000 or more MAC addresses on the individual port. Now, this could also be used, the port security, to stop people from bringing their own hubs or switches into the network to try to plug in more devices. So even if we do not audit the network based on the specific MAC address that is supposed to be on the port, we can simply just put a hard limit as to how many MAC addresses. So let's say that we have an environment that does not have IP telephony, and we're using all full duplex switch ports. That should imply that each host-facing port, each edge port, only has one MAC address on it. So we could put a simple filter that says only allow one MAC. If you go above that, just drop all the traffic from the other MAC addresses. Okay, our next solution to prevent some of these type of problems is to first off make sure that the user is legitimate and they're supposed to be on the network in the first place. Now, this is a very common protocol that is used with wireless authentication, known as the 802.1x authentication suite. Okay, .1x is used in wireless with things like EAP and Cisco's Leap authentication to forward requests to a centralized authentication server known as AAA. So, authentication, authorization, and accounting server through the protocol Radius. It's remote access dial-in user services for authentication. So basically what this protocol suite does, 802.1x or simply .1x, is that when someone plugs their cable into the physical wired LAN, the switch sends them a challenge, a password challenge, that has to be authenticated with the Radius server. So this assumes that the user's laptop or the user's desktop has some sort of credentials that is going to allow them into the network at the same in the first place. So this would prevent any type of DHCP starvation or any type of basic layer 2 spoofing or layer 2 man in the middle, because the user would have to already have authentication credentials to get on in the first place. Okay, another possible way that we could make the layer 2 segment more secure is with a feature that is known as private VLANs. Now, the logic of private VLANs is very straightforward what it is trying to accomplish. The problem is Cisco's implementation, it gets a little bit confusing as to what the different terms that they're using. Okay, but the basic principle is this. Think about how the network works in a hotel when you're in one of the hotel rooms and you're plugged into their physical wired network. If you were designing that hotel network, you would want to set it up so that users in different rooms cannot talk to each other, but they could talk to the default gateway in the network. So even if the rooms on, let's say, rooms on floor 10 are all in the same VLAN and all in the same IP subnet, we want some sort of security configured in a way that traffic cannot pass directly between the rooms. It would have to go to the default gateway first. And that's the exact logic that private VLANs are trying to accomplish here. So we're taking a regular access VLAN that would normally span a single subnet, and we're breaking it into smaller VLANs in which we can control exactly what ports can talk to each other. Now, this is also a common design in shared hosting environments, where you have a colocation service that someone is hosting websites for different people. Based on their IP address allocation, they don't want to have to create a subnet for every single server because they're going to burn up at a minimum 3 additional addresses to give each server a unique subnet. It would have to be a /30. It would be the network, the broadcast, the gateway, and then the server itself. So what you can do with this type of design is just put everybody in the same subnet, but then define the individual private VLANs or these sub-VLANs so that the individual server ports cannot talk to each other. They can only talk to the default gateway. And additionally, what's nice about this feature is that it can span multiple physical switches. So if multiple switches in a row agree on what the private VLAN assignments are, the devices do not have to be all on the same physical switch. Now, the way that this is accomplished implementation-wise is first off, we take our main VLAN, which is called the private VLAN, and we're going to break it down into 2 sub-VLANs. These 2 sub-VLANs are either community VLANs or isolated VLANs. Now, a community VLAN, anyone who has a port that is assigned to the community VLAN, they are allowed to talk to other devices in their community along with promiscuous ports. So let's say, for example, that we have 2 web servers that are supposed to talk to each other and the default gateway. We would put the default gateway as a promiscuous port, so it means it can talk to everybody. Then the 2 web servers would be in the same community VLAN. So they can talk to other ports in their same community and to the promiscuous port, but they cannot talk to anyone else. Now, the isolated VLAN is going to be for anyone who you want to allow them to talk only to the promiscuous port. So these might be separate customers that you don't want them to talk to anybody except the router. Each port, you put that in the same isolated VLAN, and they're only allowed to talk to the promiscuous port. Okay, so let me draw out a diagram here. It'll be a little bit easier to visualize this. So let's say that we have a switch here, that on the top we have it connected to the router. That's going to be our default gateway. And then we have a bunch of different clients that are attached to switch. So we have A, B, C, D, E, F, and G. And then we have router 1's port. Now, under normal designs, we would specify that router 1's port is a promiscuous port. This means that it can talk to anybody that is in the private VLAN. So it can talk to A, B, C, D, E, F, G. There's no restrictions. Now, for A and B, We are going to put them in a community. And we'll say they're in community VLAN number 10. C and D, we're going to put them in community 20. Then E, F, and G, we're putting them in isolated VLAN 30. So what this means, first off, is that everyone will be able to talk to the router. Everyone is always going to be able to talk to the promiscuous port. Devices in community 10, so A and B, they will be able to talk to each other, plus to the router. C and D will be able to talk to each other, plus the router. Then E, F, and G, they will be able to talk only to the router. But the key here is that everyone normally would be in the same IP subnet. So we'll say everything is 10.0.0.0/24. So we don't need to worry about splitting up the layer 3 segmentation. We're bringing this segmentation down into layer 2, into the VLANs. Now, in order to do this specifically implementation-wise on the Catalyst switches, it requires that the switch be in VTP transparent mode and that you use extended VLAN numbers. So we have to be in VTP transparent mode in order to allow the private VLANs. Actually, technically, you don't have to use extended VLAN numbers, but when you are in transparent mode, you are allowed to use extended VLAN numbers. So since you can have a lot of VLANs created to get a complex policy for the private VLANs, a lot of the times that's where those extended numbers are going to come from. Because every community would have to be its own VLAN number, and then the isolated VLAN, there would be one isolated VLAN per private VLAN. Okay, so as I mentioned, we're not going to do a lot of configuration examples with these security features, but you may want to know where this stuff is documented. So you could either try it out yourself or at least look at the syntax examples that are on Cisco's website. So if you go to your web browser and go to the main Cisco webpage, go to support, and then to, actually let me go back. So the main webpage, support and configure. This is going to bring us to the product documentation page. From here, we'll go down to switches, then to, security switches. Switches, LAN switches. Let's say, for example, Catalyst 3560. Most of these are going to be pretty much the same, the iOS-based switches. Then to configuration guides, we'll pick the iOS version. Let's just say we pick the latest one, 12.2.52. Then we'll see the individual topics listed on the left. So security topics here would be 802.1x port-based authentication. So this is for configuring the switch to talk to the Radius server. For configuring private VLANs. Configuring DHCP features and IP source guard, and configuring dynamic ARP inspection. So these two are going to work together. Then configuring port-based traffic control. So port-based traffic control would be things like port security, and then how to limit broadcast storms and unicast storms, a feature called storm control. Okay, then also configuring network security with ACLs. This would be for VLAN access lists. And we'll come back at a later time and get back to VLAN access lists. We're going to show a bunch of implementation examples when we get to some other topics later in routing and in troubleshooting. So we'll definitely come back and hit on that.